Namaskaram. Today we are going to discuss dual simplex method. In last class we have seen the simplex method. In simplex method, actually the initial solution is feasible but not optimal. Okay. But in the case of dual simplex method, the case is different. The initial solution is actually better than optimal but not feasible. Okay. That means, suppose this is our feasible region of solution and this is our optimal solution. In the case of simplex method, we are starting from a solution somewhere here. So this is feasible but not optimal. So after some iteration, we will reach this solution. Okay. In the case of dual simplex method, again, suppose this is our feasible region. Then we are starting from a better solution. That means maybe the solution is somewhere here. Okay, this solution is better than this one. Suppose our problem is minimization of z. Maybe actual minimum value is 10. This is maybe some 5. Okay, that is the meaning of the initial solution is better than optimal. But the solution is not feasible, not in the feasible region. Okay, that is the situation. So after some iteration, we will reach the same solution. That's the idea. Okay. Okay, then there is a natural question. What is the advantage of dual simplex method? Uh, so the main advantage is this method is applicable when all the constraints are less than or equal to, as similar to our simplex method. But we have one extra condition with at least one RHS is negative. Okay, we have seen that in the case of simplex algorithm, and the simplex method is applicable, the standard form contains only the slack variables, that is constraints are all less than or equal to with the positive RHS. Okay, so simplex method is applicable only when all the constraints are less than or equal to type with the positive RHS. Okay, if at least one RHS is negative, then you can apply simplex algorithm. So in such situations, you can apply a dual simplex method. Okay, that is the advantage of dual simplex method over the simplex algorithm. Okay, so dual simplex method is applicable when all the constraints are less than or equal to type with at least one negative RHS. This is the standard form of dual simplex method, similar to our simplex algorithm. Objective function should be in maximization type. If it is minimization, we know how to convert it in a maximization type, and convert greater than or equal to type inequalities into less than or equal to type by multiplying a minus sign, and introduce only slack variables, because first of all we convert everything into less than or equal to type equation, so we have to introduce only slack variables. And how to convert minimization to maximization? Suppose our problem is minimize z, then we know that is we have to convert that is equal to maximization z star means what? That is equal to minus z. Okay, already also we know that the minimum of z is equal to minus of maximum z star. Okay. Okay, next we are going to see the algorithm, the dual simplex algorithm, similar to our LPP, almost similar to our not LPP, almost similar to simplex algorithm. The first one is if at least one Cj minus Zj is positive, then this method is not applicable. Okay. Okay, you can evaluate our Cj minus Zj using these formulas, because we know Cj's are the cost, and you can evaluate Zj using this formula. They are all similar to our simplex algorithm. Okay, already we are familiar with this Zj and Cj minus Zj. They are all same in dual simplex method. Okay, what is Zj? You take this cost into corresponding first element plus second cost into corresponding second element, like that. Okay, so that's why this is sigma CBI AIJ. Okay, so that means if at least one Cj minus Zj is positive, then this method is not applicable. Clear? Then next one, if all Cj minus Zj less than or equal to 0 and xb is greater than or equal to 0, then the solution is optimal. The present solution is optimal. All the Cj minus Zj's are less than or equal to 0 and xb. What is xb? The present value of the basic solution. Yes, in this table it is clear that this column represent xb. Okay, so this is the present value of basic variable. Whatever be the variable in this table, that is their basic. So this is the corresponding value of the basic variable. Okay, so this is clear. If all Cj minus Zj less than or equal to 0 and xb also greater than or equal to 0, then the solution is optimal. Then Next one, if all Cj minus Zj less than or equal to 0 and at least one basic variable is negative. If all the xb's are positive, then that is optimal solution. If at least one xb is negative, then select key row with the xbk. What is xbk? It is a minimum of such negative xbi's. Okay, suppose we have minus 2, minus 5, 1. Suppose these are the present basic solutions. Then here at least one negative is there. Then choose the minimum one. So in this case, this is the minimum, right? Suppose this is our column corresponding to xb. Okay, then we can choose this row as key row. Clear? Okay, in this case, there are two sub cases. So now we choose the key row. Okay, so next we have to identify the key column. That means entering variable. Now this is the living variable. Next we have to identify the entering variable. Okay, so there is a first case is if all akj j equal to 1 to n are non-negative, then no feasible solution. So here akj means the terms corresponding to this row, that is akjs. If all the akjs are non-negative, then no feasible solution. Okay. Otherwise means what? Otherwise means at least one negative is there. Suppose this row contains some minus 1 or something like that. At least one negative entry belongs to this row, then you can find this ratio Cj minus Zj divided by this negative element. Okay, that is our next row Cj minus Zj by Akj with the negative Akjs. Okay, suppose we have two negative elements in this row, then you take the ratio corresponding to only these two. That's all. Okay, then take the minimum. Suppose this ratio is like this, some minus 1 and minus 7, then the minimum is minus 7, like that. Okay, so this is the column correspond, this is the key column. Okay, so that means this variable will enter the basis and this variable is leave the basis. Okay, so we know this element is pivot element. Once you identify the pivot element, then all the remaining procedures are same as in our simplex algorithm. So we make this pivot element is 1, then using this pivot element we have to make all other entries are 0 in their respective column. Okay, they are all same as in our simplex algorithm. Okay, so repeat the procedure. This is the algorithm for dual simplex method. Okay, let me explain this procedure with this example. Minimize z is equal to x1 plus 2x2 plus 3x3 subject to the constraints. Okay, here the variables are non-negative. So first we have to convert the problem into maximization. So we know how to convert maximization. The objective function is z star. What is z star? Negative of this one. Okay, that means minus x1 minus 2x2 minus 3x3. And also we have to convert every constraints into less than or equal to type. So this one is already in less than or equal to. So we have to multiply a minus 1 with these two. Then only it will be in less than or equal to type. Okay. So this become like this, minus x1 plus x2 minus x3 less than or equal to minus 4. And there is no change in second one. And this become minus x2 plus x3 less than or equal to minus 2. Next you have to add the slack variables. Okay. So here plus s1, then here plus s2, here plus s3. Okay, so this become equation, they are equations, so equal to. So you can convert this is like this. The maximize z star equal to minus x1 minus 2x2 minus 3x3 subject to the constraints minus x1 plus x2 minus x3 plus s1 equal to minus 4, and this become x1 plus x2 plus 2x3 plus s2 equal to 8, and this become minus x2 plus x3 plus s3 equal to minus 2. Okay, so this is the standard form for applying our dual simplex method, because all the variables are slack variables and at least one RHS is negative. So you can apply the dual simplex method. So now we are ready to write our initial table. So this is the initial table. They are the cost corresponding to our variables. They are the decision variables. They are our slack variables. We know the cost corresponding to slack variables are 0. And in this is the row corresponding to s1. Initially our basic variables are s1, s2, s3. Yes, we set the cost corresponding to the slack variables are 0. Okay, like that 0 S2 plus 0 S3. Because we are not interested to affect the new variables in our objective function. That's why we put the cost are 0. Okay, also, how to find the values of basic variable by substituting n minus r variables. Here, n is the number of variables. Now we have total 6 variables. R stands for number of equations. Here there are only sorry, not m in standard form m. We have only 3 equations. So we can substitute 3. We can choose 3 variables are non-basic and remaining are basic. Okay, so here we normally we choose this decision variables are non-basic. Initially we choose decision variables are non-basic. So we are going to choose x1 equal to x2 equal to x3 equal to 0 because they are non-basic. And what are the basic? So the basics are s1, s2, s3. Then how to solve? If x1 equal to 0, x2 equal to 0, x3 equal to 0, then s1 equal to minus 4, right? Similarly, if x1, x2, x3 are 0, so s2 equal to 8 and s3 equal to minus 2. So this is the procedure for writing our initial simplex table. So this is the value. So they are the basic variables s1, s2, s3. This is the corresponding cost, and these are the values of basic variable. These are the initial values of the basic variable. Okay, this matrix, this system corresponding to our equations. Okay, constraints. Okay, next we have to calculate Zj minus Zj. For evaluating Zj minus Zj, Cj's are there. First of all, we have to evaluate Zj's. That means Z1, Z2, Z3, Z4, Z5, Z6. Okay, how to evaluate Z1? I will show you one. Yes, we know that we can evaluate Z1 using this formula sigma CBX1. That means 0 into minus 1 plus 0 into 1 plus 0 into 0. Okay, that is a formula for evaluating Z1. Once, initially this Z1 equals 0 because all the codes are 0. So then what is Z1 minus Z1? Here Z1 is minus 1 and Z1 is 0. So minus 1 minus 0 minus 1. So the first entry is minus 1. Similarly, you can evaluate all the Cj minus Zj's. Okay. So these are the Cj minus Zj's: minus 1, minus 2, minus 3, 0, 0, 0. Okay. And this is our procedure. If all Zj minus Zj less than or equal to 0 and at least one basic variable is negative, then select key row with the negative minimum of xbi. Okay. Yes, this table satisfies our condition. All Cj minus Zj are less than or equal to 0. Minus 1, minus 2, minus 3, 0, 0, 0. It satisfies this condition. And at least one xbi is negative. Yes, we have two negatives. This is less than 0. This is also negative, less than 0. Then how to choose the key row? Key row is the minimum. Minimum of minus 4, minus 2. In this case, minimum is minus 4. So you have to choose this row as our key row. Clear? So I'm going to choose this row as key row. Next, that means this basic variable s1 will leaves the basis. So next we have to find the entering variable. Okay, that means we have to find the key column. How to find the key column? Okay, this is the procedure for finding the key column. If all akj j equal to 1 to n are non-negative, that means the elements corresponding to that the elements corresponding to the key row are non-negative, then there is no feasible solution. Otherwise, suppose at least one negative is there in that particular key row, then we have to find cj minus zj by then the corresponding negative akj, then take the minimum. That is our key column. Okay. Yes, this is the row corresponding to these are the elements corresponding to our key row. Yes, it contains two negative entries. If all the entries are non-negative, then there is no feasible solution. But here it contains two negative. Okay, so next we have to find the ratio. So there are two ratios. One is minus 1 by minus 1, other is minus 3 by minus 1. Okay, so this one is 1 and this one is 3. Then we have to choose the minimum. Out of these two, minimum is 1. Okay, so this is our key column. Key column means x1 will enter the basis. Presently, x1 is non-basic. In next iteration, x1 is basic. And S2 will leaves the basis. Okay, that means S2 is non-basic. Okay, then what is our next procedure? Next, we have to identify the pivot element. So this is our pivot element. Then all the steps are same as in simplex algorithm. Okay, so next you have to convert this entry is one. Using this and using that one, we have to convert every element in these rows are zero. The elements correspond to this column are zero. Okay, that is our procedure in similar to our simplex algorithm. So to convert this minus 1 as 1, we have to multiply this element with the minus 1. Before that, we have to remove this non-basic. So what is the variable, which one is the variable in the first row? So S2 will leaves the basis and X1 will enter the basis. So here it is X1. And what is the cost of X1? The cost of X1 is minus 1. So this is the change in this portion. Okay, there is no change in these two variables. There is no change in these two variables. So next we have to multiply a minus 1 with this much of entries. Okay, so this is 4, this is 1, this is minus 1, this is 1, this is minus 1, 0, 0. Clear? Okay, so yes, these are the changes: minus 1, x1, 4, 1, minus 1, 1, minus 1, 0, 0. Okay, then using this one, we have to convert these two elements are 0. There is no, already this term is 0, so there is no change in this row. And how to convert this element is 0? Using this one. Okay, so the R2 goes to R2 minus R1 new. Actually, this row is R1 new, right? This is our new R1. This is our new R1. This is our R2. Okay, here R2 stands for this one. This is our R2. So we are going to apply this rule, R2 minus R1 new. So 8 minus 4, that is 4. Clear? And similarly, 1 minus 1, 0. 1 minus minus 1, that is 2. 2 minus 1, that is 1. 0 minus minus 1, that is 1. 1 minus 0, that is 1. 0 minus 0, 0. Clear? There is no change in third one because already this term is 0. So this is a new table. Okay, next we have to find Zj minus Zj as similar to the previous case. So in this case 0, minus 3, minus 2, minus 1, 0, 0. Then here some xb's are negative. So there is only one negative xb. So choose the minimum. So this row is our key row. Then you have to take the ratio corresponding the negative entries in this row. In this row there is only one negative entry. So we have to take only one ratio, that is minus 3 by minus 1, that is 3. So there is only one entry. So this is the minimum. So this is our key column. So now we have a pivot element. So this is our pivot element. Next you have to convert this pivot element is 1 by multiplying a minus 1. And also one more thing in this case, which one is entering variable? Yes, in this case, this x2 will enter the basis, right? And this variable leave the basis. So this variable leaves the basis. That means this will become non-basic and this will become basic. Clear? To convert this minus 1 as plus 1, you have to multiply with a minus 1. So this is 2, 0, 1, minus 1, like that. And instead of s3, this become x2. And what is the cost of x2? The cost of x2 is minus 2. So these are the changes in first iteration. Third iteration is minus 2, x2, 2, 0, 1, minus 1. Okay. Then we have to convert this term becomes 0 and this term becomes 0. How to convert this term becomes 0? That is R2 goes to R2 minus the, what about the element, this element in new R1, that is 1, right? So R2 minus 2 times R1 new. Clear? R2 goes to R2 minus present, in present R1, here it is 1. Okay. So R2 goes to R2 minus 2R1. What about R3? It is minus 1. In new, sorry, one more thing. One second. Actually, this is not R1. This is R3. Okay, this is R3. So R2 goes to R2 minus 2 R3 new. And similarly, what about R1? In R1 it is minus 1. In new R3 the time is 1. So that is very simple. R1 goes to R1 plus R3 new. Clear? So these are the two elementary row operations. So after these two operations, the table is like this. Okay. So next we have to find Zj minus Hj. Here Cj minus Hj's are like this. Yes, now all the Cj minus Hj's are less than or equal to 0 and all the xb's are greater than or equal to 0. So this is the condition of optimality. Clear? So since all the Cj minus Hj's are less than or equal to 0 and xb's are greater than or equal to 0, so the present solution is optimal. So what are the values of our decision variables? X1 equal to 6 and x3 equal to 2. So what about our x3? In present table, x3 is non-basic, right? X3 is non-basic, so its value is 0. So these are the values. So the optimum solution x1 equal to 6, x2 equal to 2 and x3 equal to, oh sorry, this is not 3, this is 0 because x3 is non-basic in this last table. Okay, final optimum table. So this is the optimal solution x1 equal to 6, x2 equal to 2 and x3 equal to 0. So what is the value of our objective function? Our objective function is either you can evaluate the value of the minimum or value of the objective function, minimum value of objective function. Either you can substitute x1, x2, x3 in this equation. Okay, so in this equation, what happened? So what is the minimum? So minimum of z is equal to x1. What is x1? X1 is 6 plus 2 times x2. X2 equal to 2 and this is 0. X3 equal to 0. So that time is 0. So 6 plus 4 that is 10. Okay, so you can find directly from this minimization or you can find this minimum using this relation. Which relation? Minimum of z is equal to minus of maximum of z star. Okay, so you have to substitute this 6 and 2 in this expression, that is 6 and 2 and 0. So its value become minus 10 and there is a one more minus. So minus of minus 10, that is plus 10. Anyway, the minimum value of z is 10 at the point 620. Clear? That's it. Okay, so this is the idea of dual simplex algorithm. Thank you.